Hi everyone, my name is Mengchuan. I'm a postdoc at University of Strathclyde, and the work I'm going to present today is my PhD work at University of Glasgow, UK. So it is my great pleasure to join this conference. Let's get started. I'd like to share my screen first. So the work I'm going to present today is Sapphire long period grating fiber for potential refractive index sensor. Here's the outline. I'd like to discuss background and fabrication experiment, and then summary and follow-up research. So I think it is fair to say optical sensor has many advantages over electronic sensors, and the fiber optic sensor is one of the optical sensor, and it is many advantages over conventional electronic sensor, for example, small size, lightweight, and immunity to the electrical and magnetic interference. But for the harsh environment sensing, it is always a challenge for high temperature, high pressure, and chemical aggressive environments because of the material limitation of the optical fiber. So here's why we study single crystal fiber, because a single crystal material have many advantages, such as high melting point and hardness, extremely hard, and excellent transmission range, also resistant to corrosion. So we try to use this single crystal material to create single crystal fibers and build fiber optical fiber sensor on the single crystal fiber for harsh environment sensing. So this is the start of our work. So here, let me introduce the fabrication process of single crystal fiber and the long-term grating. So first, how do we fabricate single crystal fiber? The technique we use is a laser-heated pedestal wall. So as you can see in the picture, we have a source rod that is a fiber source, and we use a high-power CO2 laser to melt the tip of the source rod, so create a melting zone, and dip the fiber seed inside this melting zone and draw the fiber. So the fiber pull rate is larger than the source feed rate, so the fiber can grow as a constant fraction of source rod diameter. In this picture, you can see this is a melt with a picture of the camera we took in the lab, and this is our fiber, and this is our setup. So this is a basic fabrication method we use. So how do we fabricate the long period grating? Because sapphire fiber or single crystal fiber is very, very hard material and very high melting point. So conventional fabrication for long period grating cannot be applied to the single crystal fiber. So this is always remain a challenge. So the previous technique for long period grating on single crystal fiber is precision dicing, that you use computer controlled diamond saw and continuously cut gratings with a period of 150 micron. And this was done on the commercial sapphire fibers. So our proposed technique is called mechanical speed variation. In this technique, we use periodic modulation of the fiber diameter to create or to inscribe the grating on the fiber. So the grating with different periods can be broad, and we can also use different source material. So we will compare these two methods more in depth in the following points. So in our proposed method, we achieve fabrication of grating by periodically modulation of fiber diameter. So here is a schematic of the long period grating produced. And this was achieved by changing the growth speed periodically. When we increase the pull feed rate speed periodically, and when we increase the speed, the fiber diameter actually decreased. When we lower the speed of the growth, the diameter of the fiber wall become larger. So as you can see in this picture, the red dot line is the radius of the fiber diameter, and the blue line is speed of the pull rate. So our pull rate and the growth speed goes up and down in that motional pattern. The grating can be grown. And this is MATLAB illustration for the grating growth, and we use lab software to control our laser-heated pedestal growth procedure. So the advantage of this technique over the last dicing method, it is very simple and flexible technique, and we can grow large range of grating periods we don't the period of the grating won't limit it by the blade thickness. So in that cutting in that precision dicing method, and also because we glue the fiber with the grating together, so we can choose our source rod for fiber. So we can use different single crystal material and dot material for the growth of fiber, and also for the grating for different application based on their characteristics. And also we find that the result of using this technique, the grating response is more sensitive, and at last it is a cost-effective technique because you grow the fiber and grating together, not only from the raw material, but also you can save money for the grating fabrication and also commercial sapphire single crystal fiber. So here's an experiment. We use we compare two fibers. One is with grating, another without grating. We use 90 microperiod grating to do the experiment. As you can see, there's two fibers. One is with grating, 3.5 centimeters. Another is without grating, so pure straight single crystal fiber. So single crystal fiber here we use is sapphire fiber. So we use a plating oil as plate because the fiber was grown only the core, so we need to have it plated to test the long period grating effect to see if the grating light coupling into the grating is efficient and effective. So here is our experiment setup. We have a broadband light goes into the fiber and collected by a monochrommeter and analyze the data on PC. So here's a coupling response for the straight fiber. We can see that for the reference, the black line is a light source strip, and blue line is a straight fiber without plating. And once we add the plating, immersion oil, index oil in this case, so we can see that for the straight fiber, there's no change. But for the same condition for the grating fiber, we can see it is dropped at the region of 600 to 800. That indicates that the long period grating actually integrated at works. So it is a coupling effect between the incident light with the grating and partly loose into the environment. After this experiment, we also did the refractive index variation response. In this experiment, we have different liquid or index oil in this case with different refractive index value to see if it can affect the grating and the transmission spectrum. And it turns out it is very obvious, and the transmission actually shifted a lot from, you can say from the table. The cross wavelengths changed over 100 from 696 to 823, and also the intensity drop. So compared to the previous technique using precision dicing method, actually you can see the we also use the same method, adding the index oil to see if the grating the fabricate is effective. Actually, you can see that the result is not that obvious, and compared to our results, you can see the intensity drop, but after you increase the refractive index, you can also see which part drops, but it is overall intensity drop. So in this proposed technique, we observed the permanent variation of the resonant wavelengths with wavelengths varied by 130. So yeah, I think in this presentation, I think we already tasted about single crystal fiber, why we studied it. It is for touch environment sensing, and this is a preliminary result that we got for making long period grating on single crystal fiber. So we proved the grating coupling effect, and it's essentially also its feasibility for refractive index. It has a great potential for refractive index, and also with high temperature plating, it can be used for harsh environment sensing. For further research, we will focus on single crystal fiber plating for long period grating, and also other single crystal fiber harsh environment sensor. For example, black body irradiation sensor and fabric interferometer. And the last topic we like to study is distributed quantity distributed sensing for the harsh environment. So this is some picture we have already worked. in the lab to make a black body radiation sensor and for Fabrico interferometer sensor. So it is great to have an opportunity to present in this meeting, and I hope this is interesting to you. And thank you very much for your time and attention. Now I would like to answer any questions. Thank you very much.